Hi everyone, welcome to this lecture on dietary minerals. We're going to start off talking about our biological mineral needs. So first though, minerals are classified into groups, and much like the vitamins, they're called micronutrients. So we need them in very small quantities in the diet. We also sometimes sub-classify them into trace, major, and ultra trace categories, which is the way that this lecture is organized. Major minerals are needed in quantities over 100 milligrams per day, trace under 100 milligrams per day, and ultra trace minerals, which we don't talk about much, like cadmium and chromium and copper, although important, are ultra trace. We just get them and we retain them. We don't need a lot of them in the diet, and we don't discuss them too often because, like I said, we get them in water sources and our body holds them very effectively. We also sometimes see, and most often I'd say, I remember first learning about nutrition, I remember seeing the minerals and often combined with water as functional nutrients. Like you would see them categorized not by the amount of the diet, but the bone minerals or the electrolyte minerals. So of course we'll talk about these functions in component 4, but it's often a way they're classified. They're also sometimes classified by dietary source, and we'll touch more on this in part 2, but natural minerals versus added minerals. And so added minerals are, an issue when it comes to things like sodium, which are only from added sources, and also important for good nutrients like added ferric acid, which is a form of iron that's, we use to enrich, that's important, but it's all added. Also, we can look at the difference between plant and animal sources because they do differ in their bioavailability in our body. So you can, like, for instance, calcium, it's mostly from animal sources, which is more bioavailable. Iron, half and half, like half the iron we get is from plant sources and a little bit less actually is from plant, but a little more is from animal sources. Potassium, you can see that's almost all plant sources because we don't get a lot of it from animal foods. So that's sometimes a way that minerals are grouped. Now, on to the intake guidelines, which again are just world-based. World health experts come together to establish these guidelines, published in the DRI. Everything they do is based on average adult-sized men and women with average calorie intake. They have a few books in the DRI for 15 minerals. 6 of them are major. I'm going to say that because we organize the lecture this way, but 9 are trace. The DIR minerals are classified as the bone minerals. This book includes calcium, phosphorus, the bone minerals. Also I'm not sure why, but it looks like trace, ultra trace vitamins with the fat soluble vitamins A and K. I would say because they're both micro, like nano, not milligram, but microgram quantities, but that wouldn't completely fit. And then there's sodium, potassium, or the electrolyte minerals. So looking first at RDAs, which are again better established values. The RDAs for major minerals include magnesium, phosphorus, and calcium. And for the trace minerals, you can read those, but lots of different methods to determine our daily needs for these. For instance, in lots of different countries where they don't iodize salt, like here we put iodine in our salt. So we use salt. As we'll clearly come to know at the end of this lecture, we use salt. We get plenty of iodine, but in places and before we iodize salt, the thyroid gland would enlarge and people would have goiter and you'd be able to say iodine deficiency. So our daily needs for iodine deficiency were based on the amount needed, so that goiter so that your thyroid health and size could be perfect. I love the minerals, iron, calcium, and zinc. And again, just kind of like our body is so smart with these minerals because it only absorbs them proportionally to the amount that it's needed. So you can measure the blood levels, you can measure the absorption rates, and you can know exactly how much is needed per day to just maintain that perfect balance. Everything excess that the body doesn't want is obviously excreted. So they're able to do balance studies, feed a known exact amount, measure how much comes out, and go, that's how much they took, and then create neat, tight lines with how that changes the blood. And they're very tightly related. They're proportional. Adequate intake, less, real concrete evidence besides these, except for just average healthy adults who don't have hypertension, all the things are fine with this level of intake, healthy teeth, healthy bones, etc. There are upper intake levels established, and we'll talk about these more in component 5, but they are part of the DRI set. So I always put them here as just to touch on the minerals that we do sometimes consume in excess amounts by either supplemental levels, additives, or just by accident, like swallowing toothpaste. There also are lots of upper levels established. I just have to put out for the trace minerals, which again, we don't discuss too much, but these are established by the EPA, not really dietary guidelines, but more in the realm of water health and, agricultural soil health, because these are ones that we get from those sources. Dietary guidelines for Americans care a lot about salt. The last couple iterations, which are 5 to 10 years long, I kind of forget. I think they're a decade, but I think I'm thinking of healthy people. I think they're 5 years. Yeah. Every year there's something about sodium. It's a big worldwide objective, but nationally in this dietary guidelines for Americans, they're trying to reduce sodium intake. It's really all over the place. The World Health Organization also again has a worldwide goal to reduce salt intake for the whole population by 2030 by 5 grams, which is equivalent to 2 grams of sodium. And so this is a good time to distinguish, because as a student, I was so like, this is wrong. I could never understand the difference in salt and sodium. And so I would look at things and be like, how could that possibly be right? Salt is a collection of chloride and sodium together. So salt is, about 40% sodium and about 60% chloride. So when you're having a tablespoon of salt, it's only 40% chloride by weight. But gosh, that was confusing by me. So salt less than 5 grams, that's really the World Health goal, but I just added what that is in an equivalent, which is less than 2 grams of sodium. But still notice that the World Health goal, less than 2 grams, is still a little higher than the DRI, which is 1,500 milligrams. Let me see if I can go back right there, 1,500 milligrams per day. So it's a little more conservative on the DRI than the World Health goal, but it's smart to not go too crazy with a goal, because right now we're like at 2 times the level we'd like. So let's start with baby steps. But that's the world's goal. We have lots of different extrinsic behavioral things, we're on the behavioral portion, that affects our mineral intake. And so they're important because they're what's going on that influences what we pick up to eat, but they're behavioral based. They could be goals, like for strong bones, I'm going to take calcium supplements, lots of sodium from snacking, cultural foods, and from just different customs. If you live in the US, you're going to get a lot of salt preserved foods, unfortunately. Lots of different variations in salt intake by age, gender, race, socioeconomic patterns. So it is legit difficult to combat because the groups are hard to target. It's all over the board in terms of targeting high salt intake. The government has stepped in on minerals in one area, which the irony of it is that the concept of these enrichment programs were really nice because we had taken and figured out a way to use grains from a science perspective smart and efficiently. But what happened was that we just stripped all the nutrients out of them, so we required to add them back, and it works. It's just that now we're so reliant on those mineral sources that it's just a bummer. But iron is one of those ones that we're usually going to get an adequate amount of because it's part of fortification programs, and so they have to use it in all of the enriched flour products, which are obviously snack foods, pastas, breads, and so everything we eat a lot of. We know that on the label a few things are required, like sodium. Interestingly though, 160 milligrams is based on a 2,000 milligram level, not 1,500. I just noticed that. That was a note to self, sorry. Added potassium was just required in 2017. The other two, calcium and iron, have always been there since the 1992 Act where this was first required, but that one's new now. Added potassium in 2017 because, and I'll tie this together later, but sodium and potassium are related. Their losses are related, their dietary sources are opposite, polar opposite, so we'll get to it. We also know this, and so we're trying to promote more potassium, more calcium with more fruits and vegetables, etc. But I'm getting to the point that we have influences that change our mineral intake, and part of these are these promotions that they do. Reduce sodium intake, we see it on our stuff, we see it on the kids' stuff, we see it on what the news brings out for new exciting research. Nutrition marketing. So this is another area where we see the product of food science, nutrition research, but there's a lot of FDA related claims. And they're approved, they're qualified about the importance of minerals for bone health. So the actual functional claim is calcium supports strong bones. And then they added the D, and sometimes companies will even put the phosphorus and magnesium in there, but it's not needed. Calcium's approved for helping strong bones. There's also lots of relative claims on the market, whether you notice them or not, but less than, reduced in for sodium, because we know that we're trying to reduce that. And lots about good sources of, excellent source of iron, etc. And that's kind of how we'll structure the next component 2. We'll look at just like what on the spectrum does this satisfy? Does it satisfy a good source or an excellent source? So we see those for especially iron products. So let's talk about our dietary sources, and I will try to keep it concise. I know that means fast, and so I'm sorry, I'll try to keep it slow but concise. Minerals in whole foods. We're always going to start with those, but again, to remind you, we're looking for less than 12 grams per day. It's not a whole lot. The minerals in whole foods are basically going to provide us a good source or an excellent source, but not too much more than that. An excellent's about 20% of your daily needs. So whole foods are good sources, but we're getting a lot of our minerals from additives also. Minerals in food are determined by a process called ashing, which is weird sounding, but if you think about it, it makes sense. If you combust all of the organic material, all that's left is those, inorganic elements, and then those can be further analyzed, that ash, for specific mineral content. So that's how we determine minerals in food. I've done these analysis by high heat combustions like this in furnaces, but never using wet ashing, which is using the same kind of technique, but chemical methods instead of heat. Anyway, see, I'm already doing it. I cannot help myself. I just love the topic. I'm sorry, I'm already doing it. Plants and the minerals that are in plants are not that bioavailable. So it's an important distinction. I love the mineral plant or the plant animal setup in this section because minerals in plant foods are bound to organic acids. Phytic acid, oxalic acid, and later we'll look at how those are in the intestines. Just they're these inorganic compounds we can't absorb. So it's a problem. They're not that bioavailable. In fruits, though, there are a lot of minerals present, and some are bioavailable. For instance, in dried fruits and things like raisins and dried apricots, you're going to get a good amount of phosphorus and a good amount of potassium, which is pretty well known in fruits like bananas and maybe not as well known, but avocados. Also interesting to know, it's the time to introduce bicarbonate. The reason that potassium is so adored in fruits and vegetables as the way to promote, anti-hypertension is because it's usually accompanied in fruits and vegetables by a high amount of bicarbonate. And those two things together are important cell buffers. So we'll get more to that in a little bit, but potassium in fruits and veggies, which is here, are also rich in bicarbonate. Potatoes are pretty well known also for potassium, maybe not as much as bananas, but in my world they are. When my kids are acting tired, I'm all, you need a baked potato. I know they probably think I'm crazy for sure. Food people, nutrition people usually are a little on the borderline, but people thank you later, right? Anyway, I digressed. Again, only one slide later. Spinach is also a good source of dietary minerals. It's super high in, zinc, calcium, and iron. In terms of its relative contribution, it's really high in water and it's fluffy. So 1 cup of it isn't going to nail it in your daily needs, but in terms of its packed volume, it is relatively rich in a lot of different minerals. Grains are okay in minerals, but mostly the bran layer. So if you guys remember the talk on the bran, that's what's high. And so if you're eating whole grains, you're getting minerals from them, but if you're eating any kind of processed grain, not so much. The rice bran is the richest, wild rice bran particularly, but regular wild rice in its whole form provides about 1/8 of the day's need for zinc. So not crazy again, but fairly, once we eat a few servings of these grain-based foods, then it contributes a pretty fair amount. That's what the kind of origin of the good source is by the time you've had several of those portions through the day. Nuts, seeds, beans, and legumes are also a great source of iron. Really good source, actually. 1/4 for a 1/2 cup serving of hyacinth beans, and other types of beans are comparable. But nut butters are really good, especially peanut butter, because kids like it and it's relatively inexpensive. They, enrich it with iron, ferric acid, to make sure that it meets people's day's need for iron. Tofu and any kind of meat alternative that's lightly processed, like from the legume family, is going to be high in calcium. Lots of nuts are high in phosphorus, which you did not know this. Oh, I just said potassium for tofu. I meant phosphorus. Whenever you think of calcium, think of phosphorus. They're a couple, they go together. And sodium. You guys probably knew this, but I'm a big baseball fan. Well, you didn't know that, but you knew sunflower seeds were high in salt because that's all they really are, is like a little salt vector with a little delicious seed in the middle, but they're high in salt. They provide a ton of things, salt in the diet, those salted and roasted nuts. So animal minerals are more bioavailable because they're bound to proteins. So they bypass all of the other things that would bind them and they get right to the intestines for absorption. So the best sources of iron in the diet include organ meats and tissues like beef. Beef is a great source of zinc, and the liver and spleen of animals like chicken, turkeys, and cows are excellent source of the mineral iron and zinc. So we'll get to it in a little bit, but these are our iron storage depots, so it makes sense that dietarily they would be a good source. Also kind of makes sense intuitively with ocean waters being so mineral rich that seafoods and shellfish are our best source of a lot of minerals, but specifically zinc. Like one serving is like 100% of your daily needs. And also, by the way, look where we've just landed on the sources spectrum. Everything so far has been really relatively like kind of high on the 8th to 10th to maybe a quarter of the day's needs, but that one just met 100%. So zinc, like shellfish, is a fantastic source of dietary minerals. Unfortunately, onto that, those circles are also, you're pretty high up on the scale for sodium in these processed meat foods like sliced turkey meats, things for sandwiches, because they're meant to last. They're meant to last in the fridge or, in the case of jerky, even on the shelf. And so we use salt to do that. And just real quick, scientific, because I haven't diverted for at least a slide or two, they add salt to foods because it reduces the amount of water in them so that the microbes that would otherwise grow in there it's not available to them. So those microbes are inhibited from growing because of the lack of water activity, and that's why salt preserves food. And then it also is a cheap way to make it taste better too. So it has like lots of different functions. And I could go on, but milk is also a good mineral source. Cheese provides a little less than milk and yogurt, but only just by a function of that we only consume an ounce instead of a whole cup or an 8-ounce serving. Cheese though is really high in sodium, so I always pay attention to that one. I love cheese, but it's up there. Also, all of these, remember, if you think calcium, it's going to come with a good amount of phosphorus, so lots of good phosphorus in there too, unless it's added calcium, which we'll get to. In minerals and processed foods, because sometimes we do see added calcium in foods. We may not know that it's added, but it is. Let's see. We first talk about flours and meals, and this isn't really something that you can compare in your own diet because we don't eat flour like we eat bread, but I just wanted to show you like the difference between a 100-gram portion of wheat flour in the enriched versus unenriched forms. It's like 5 times more. So this is why these products are important, to get iron for certain populations, because if you eat 2 slices of bread and a serving of pasta, it's going to make a difference if they're enriched or not. Also, there's tons of different foods that we extract and process for their, derivatives. Like we take these sea products that are rich in minerals like calcium and zinc, we process them into powders that we take and we use in supplements. So spirulina and agar are both good examples of products that are mineral rich and derivatives and used for different things. Spices are really high in minerals, and in this case I only pointed out, I put iron, I forgot, I thought these were both salt related. Thyme, for instance, is really higher in iron, and something like chili powder would be really high in salt. And these ones are always difficult to, like when you're trying to figure out how much salt someone's taking in, these are the little things that are kind of like the hidden ones. They're like, I make really good tacos. Do you ever add salt to them? Never. I'm really good about adding no salt. I only use chili powder, and I'm like, what kind of chili powder? So, the conversation, these are hard to find, but they're also sometimes good sources of nutrients. Also, there's tons of sodium in our additives. Look at this, is probably 1/10 of the amount of sodium-based additives that are used for a number of functional reasons, most being for preservation. Even in spices, and like I just mentioned, it binds up all the free moisture and it reduces its availability for oxidation, spoilage, and microbiological activity. We also get minerals from product formulas like bottled beverages. They're used for adding tartness and sweetness, and for, again, preserving. Phosphorus, where do we get those little bubbles? That phosphocarbonate stuff that we drink and we feel, that includes phosphorus. So those ingredients that carbonate products include phosphocarbonates, and so phospho is included in them. Potassium is also from juices. Lots of fruit juices have lots of potassium, but they also have a lot of added calcium. For some reason, adding calcium to juices just exploded, and also adding calcium to milk alternatives. So you're going to see the same amount of calcium in a soy milk or an almond milk that you're going to see in a cow's milk. So they try to mirror that nutritional profile in terms of its calcium phosphorus content. So if you look at the ingredients of like a soy milk, you'll see on there like a calcium citrate or a calcium carbonate, and that's how you know that it's added calcium. Processed grains, like we mentioned, are a good source of iron and, for instance, zinc, but again, only in multiple servings. 2 servings of bread, 1 serving of pastas, etc. Cereal's great though, and I could argue I could do a great debate on myself about pros and cons of processed grain-based breakfast cereals. Let me tell you, I've been so happy that my kids aren't that loving them for whatever reason, because I literally grew up on them. So I've been in favor of them because I've been luckily without breaking tons of bones, and I don't know, just knock on wood, but whatever. I've always been like, it's the cereal. And then there's a decade of research about GMOs and glyphosates and processed corn, and oh my gosh. And so anyway, I'm holding my breath on for my own health, but glad my kids don't eat them. But on the terms of nutritional efficiency and nutritional balance and guidance, these things provide, look where we are on that scale again, like shellfish, but nobody lives on friggin' oysters and mullets all day. We eat cereal because it has a ton of these nutrients, and for whatever reason, people like it, and that may be part of the reason they like it. Also, it's sweetened like crazy, but maybe there's more of reason that our body craves it. Anywho, lots of different sodium additives in pretzels, sauces. These are another little hidden one where people will have no idea, and they're like, my favorite thing's barbecue, but I don't have any added salt in my diet. I'm like, barbecue salt, sodium, oh god, that's so much salt. Dietary supplements, just peeking at these for a couple different terms you might see on packages and about the amount that you would see provided. Usually zinc and iron supplements are aiming to satisfy all of your daily needs. Most often magnesium, calcium, less, 1/3 to 1/2. And it's because they're big. You've seen a calcium supplement, they're huge. You have to take like 4 of them. That's why people don't like them. So they're not trying to get 100%. And plus you can't absorb a ton of it at once. It's in a saturable system, so it's in a smaller dose. You also see terms on supplements like chelated, and this means that it has some kind of light binding on the mineral so that it is unable to bind with those inorganic acids, but it's, so it's tied up, but not too tied up for our digestive enzymes to process and absorb. So chelated is a term you'll see sometimes with minerals so that they don't get bound and trapped in the intestines. Also, lots of claims about calcium sources for vegans, because calcium is sometimes recommended for vegan diets. So lots about plant calcium, coral calcium, like I mentioned, those are rich calcium sources like we saw on the extract slide. Let's talk about mineral processing, and first about how minerals are, broken down lightly. They're not fully broken down enzymatically, but they are released from food compounds and absorbed. Starts in the stomach. Some are directly absorbed right there in the stomach, but most begin their deliberation. They start being liberated from foods by the pepsin in the stomach and the hydrochloric acids. And those acids also play a big role in reducing zinc and iron and iodine. There's a few that are in these more charged forms, and they're reduced by things like ascorbic acid, which we'll talk later, but we won't. This is actually now for it. It enhances the bioavailability of iron because it reduces it. And so it takes some of the work out for the stomach juices, which as we age start being as good. So in the presence of vitamin C from orange juice or something, we're having more reducing of these minerals, more absorption of them. In the small intestine, this is complicated. I don't want to explain too much. I just want to point out a few things. Is number one being that heme iron from animals is more absorbable than non-heme from plants. Non-heme has more of a complicated transport system, conversion system, and it even takes energy to get it through the basolateral membrane. Heme iron comes in through heme transporter. It's simply brought across. It doesn't take energy. It immediately connects with the blood carrier and it becomes transferrin, which is what we can measure in the blood for iron. So it's much simpler, and we have a much higher proportion of heme iron absorbed and actually transferred through the basolateral membrane. Calcium, you can kind of affiliate, again, phosphorus and magnesium with those, or definitely phosphorus and magnesium to some extent too, but they come in through a different enterocyte surface transporter. And this one's a little bit interesting because this involves vitamin D. So vitamin D, a receptor on the basolateral membrane of the enterocyte, a vitamin D receptor accepts a message from a vitamin D-based hormone that we'll talk about in a minute, but it activates calbindin right here in the enterocyte. Go ahead and pick up some calcium and bring it on in. So calcium absorption is very tightly regulated by an endocrine response that is completely dependent on vitamin D communicating with the gut cell. And I know I've just said probably way too much more detail than you envisioned when I said I won't be too detailed, but keeping it simple, vitamin D is needed to activate this calbindin, which gets calcium in. Zinc is regulated very tightly in its absorption too, comes across a zip membrane, it binds to this protein and comes in. But I put it up because it's interesting to know it's a perfect way to bring out, I could talk about mineral absorption for a year. There's so many different mechanisms, but this one's interesting because it's a perfect mineral competition scenario. If you have too much copper in the diet from, say, an imbalanced supplement setup, then you can, inabsorb other nutrients because of the competition. So this particular metallothioneine, or however the heck you say that, also binds to copper. So too much copper, you have inefficiencies in your zinc absorption. So all of these systems are complicated, but they're finicky, they're precise, they're affected by other minerals. Some are saturable, meaning they're like limited, and some can just go all day. One more thing, and then I promise to stop. Some minerals can even go through paracellularly, which is like between the cells in certain cases, and some can't. Some can only go transcellularly, like through them. So it's a really big conversation. Minerals that make it through to the large intestine are also absorbed. And this also takes place in the small intestine. So I don't want to say that, sodium, potassium, and electrolytes in water aren't absorbed in the small intestine, because they are. But in the large intestine, we also have a good activity of electrolyte exchange and water exchange. And that happens through sodium-potassium pumps. So sodium, potassium specifically are linked in that sodium comes in and potassium kind of piggybacks it. Sodium comes out and potassium piggybacks it. And it's based on this concentration gradient between inside the interior of the large intestine and the blood that's circulating by those cells in the small intestine. So it's attracted to it. And so sodium's pumped in, takes energy, and then potassium is pumped in behind it. There's also a significant amount of fecal mineral losses from, again, binding from those organic acids. Binds to phytic acid and oxalic acid to form phytates and oxalates. And we measure those in our fecal matter, and we can kind of see, gosh, there's a lot of mineral content in this, a lot of calcium content. So again, they're not always very bioavailability, but I can't help but be hopeful that that's nature's way of making sure, just like our finicky gut cells, when we do and don't absorb them, we're not accepting any minerals right now. We're good at it because we don't want to over toxify our body with minerals. And so we also, though, on that note, and last one, we also don't have to worry like a ton about mineral status. Outside of, deficient dietary scenarios, our body really is good at conserving dietary minerals. It really is. So we'll get more to that. Mineral transport and homeostasis. This is just more looking at really like where minerals immediately compartmentalize after they're absorbed. They're either into the intravascular spaces, like into the vessel. I didn't line that up very well, or the interstitial spaces. I think it's because it grew. Oh yeah, that's why. There it is. There's the intervascular space, which is like in the vascular vessel. They're also in the interstitial space, which is the space between a cell and the vessel. So any fluid in that area is the interstitial space, and then the intracellular space. And the point of this is these are the electrolyte minerals. This is where they distribute. They either stay in the blood, they go to the interstitial fluid, or they go into the intracellular compartment. And their balance and distribution across those three, I don't want to get ahead, but it has a major function. We also have minerals that we have floating around and transporting and circulating in the blood at a concentration that's very small. Only about 2% of the concentration of plasma solutes are minerals. You can see also that of calcium, which is a very important blood mineral. It's only 1% of the whole body store. So blood plasma mineral levels are very precisely and tightly maintained. except for sodium, which is one of those ones like insulin. Even though we have tightly regulated mechanisms, it doesn't always work. Calcium, on the other hand, that has to be tightly regulated, and so does potassium and many of the other dietary minerals that are in our plasma. We also have lots of dietary minerals in our red blood cells, lots in the hematocrit, heme portion, particularly iron, and so that is another area where we have iron circulating. Minerals circulating. Mineral status is maintained by gland responses and hormones, and I only put 2 up here. We could have talked about 7 or 8 or 9 of these, but I think the most poignant for understanding nutrition in bigger picture scenarios is sodium homeostasis. This is regulated by a receptor in the brain, an osmoreceptor, that senses sodium in the blood, and this triggers a number of hormones to be released, which trigger the adrenal response. And right there in the kidney, another cascade of hormones are released called the axis, because they're counter-regulatory, and it's like a lot to explain, but it causes right there in the nephron of the kidney a getting rid of or a purging of sodium because they're too high. And the brain figured that out, told the kidneys what to do, and the kidney told the cells of the kidney what to do with hormones. And the kidney goes, okay, fine, and it lets go. And we do that through our urine. So that's how sodium is released, but it starts in the brain. And I put up here, there's a race connection because African Americans may have a reduced sensitivity to salt in the blood. So as salt levels go up, everybody becomes more desensitized, I guess, to the high sodium levels. But genetically, there's an already higher sensitivity, or a threshold, lower threshold, should I say? Maybe higher threshold. It's kind of hard to explain, but they're allowed to have higher blood sodium levels without it triggering the kidney and adrenal response to release sodium. And so that's why there's a lot of hypertension in that population, and why this is an interesting subject of study. There's also a connection with potassium that relates to the exact same thing, except it doesn't boil back to osmoreceptors. It boils back to the fact that the kidneys and the nephron, when it gets rid of sodium, let me back that up, when those sodium ions go, it also takes potassium with it. It loses potassium, and potassium comes out of the cell to maintain this acidic balance, this positive negative balance, because sodium left, so potassium comes out, and then we lose potassium too. And so there's a connection, and there should be more research and better guidelines on different populations and different other dietary factors so that we can tailor salt intake better. Like, for instance, you shouldn't have 200 or 2,000 milligrams per day if you're African American or you have a low fruit and vegetable intake, because you're already particularly sensitive to hypertension. So calcium homeostasis is also pretty neat to look at, and we'll also take a peek at it again when we look at nutrition for reproduction, because the way that calcium homeostasis is maintained during pregnancy is completely, in favor of giving all of your body's skeletal calcium to your baby. So it's kind of genetically built in that we're supposed to lose skeletal mass during this time. And then post-pregnancy, we reaccumulate it quickly. So, okay, I'm getting excited and ahead, but the way that we maintain homeostasis is through the parathyroid hormone function. It senses low levels of circulating blood calcium, censors the thyroid to release parathyroid hormone. The parathyroid hormone triggers the adrenal gland to activate calcitriol. And calcitriol is a vitamin D-based compound, which is hormone-like. So this hormone-like compound travels to a few different target tissues and affects what happens with calcium. So in the case of the kidneys, at the nephron level, it says, whoa, save it. So the kidneys hold on to it, and we lose less through urinary excretion. Goes to the bone, and it tells the bone, we need some out here. So the bone immediately starts resorption processes, or bone breakdown. Remember, that was the other half of bone modeling. Oh, actually, that's coming up next. That's the bone breakdown portion of the bone turnover process. Also, it travels to the gut, and like we already looked at, vitamin D tells those receptors at the basolateral membrane, hey, tell calcitriol to go ahead and bring on in some, or not calcitriol, calbindin, to go ahead and bring some calcium in. So the action of this calcitriol from the adrenal gland lets all three of these areas adjust so that blood calcium levels are maintained. And as a result, they increase to their nice homeostatic levels of 9 to 10 milligrams per deciliter. Now, minerals are also metabolized, meaning they're used in anabolic and catabolic processes. They aren't necessarily building blocks, but they're building compounds that strengthen building blocks. So mineral containing tissues, such as those where minerals are stored. So osteocytes store most, in fact, 99% of the body's minerals. And of course, these are in our skeletal tissues of our bones and our teeth. Now, this is a lot, but iron is stored in little depots all over the body, most of it being in our red blood cells as hemoglobin, but there's also a pretty good amount distributed between the spleen, the muscle cells as myoglobin, which is just like hemoglobin in the muscles, and also in storage areas like the small intestine cells store iron, so does the liver, and it's actually recycled in the spleen, which we'll talk more about in just a few minutes at iron or mineral degradation. So proliferative tissues like the bone marrow needs lots of irons for building and anabolic activities. Most specifically, like we've mentioned, in the production of red blood cells. So this process starts with hemopoietic stem cells in the bone marrow, converting to a bunch of different, obviously, developmental forms. And in this, it's called erythropoiesis. And in this erythropoiesis process, at the erythroblast stage right there, iron is integrated into this other compound to form heme. Heme is integrated into the red blood cell in a proportion of 4 heme components to 1 globulin, which is the protein component. So hemoglobin and the synthesis of hemoglobin in the synthesis of erythropoiesis, iron is very much needed. And when iron isn't there, erythropoiesis isn't adequate, and red blood cell volume as a consequence is reduced. We also use minerals in anabolic processes like bone remodeling. Now, bone remodeling is a general term referred to for bone turnover. So this includes both the anabolic processes of bone building and the catabolic or degradative activities of bone resorption, which we already brought up a little bit because that's what calcitriol activates the skeleton to do, is start breaking up the bone to release it. So in the process of bone building, it's called bone modeling. And so it's kind of like bone remodeling, but just the modeling portion. And this is the part where we're building bone. And this happens through the action of osteoblasts. It's so intuitive to me because for me, blast, don't remember this, but blast is a word that I would think of would be like to break the bone down. But anyway, osteoblasts build bone. So I say it wrong every time I teach this subject, but osteoblasts come in and they build and lay new bone matrix. That bone matrix is mineralized. And this is where the importance of minerals comes in, because that bone matrix, which is mainly collagen, which is synthesized again by those osteoblasts or those building bone cells, those mineralization processes take place and completely change the structure and function of the bone, making it rigid, making it resistant to gravity, making it flexible and porous, etc. So the mineralization part is important for that, collagen-based matrix to turn into mineralized bone tissue. And this is exactly what I'm explaining in the bone mineralization process. Now, just like we use minerals for anabolic activities because our body is turnover in nature, we also use them for degradative activities, like in the case of in the spleen. Spleen stores iron and it also recycles red blood cells. So when iron, and I could have included this one in the homeostasis talk, but I was like, gosh, how many times can they hear that word? So we just did sodium and calcium, but iron homeostasis is pretty simple too. The spleen senses circulating levels of transferrin and other iron-based proteins, and when it senses that they're low, it starts bringing in red blood cells to break down to send iron back out into the system. So it's very neat the way our body conserves and recycles things. We also can look at the second half of the bone remodeling thing, which is bone resorption or bone breakdown. And this is done by, counterintuitive, I hate this word, but maybe you'll remember it, osteoclasts instead of osteoblasts. Why wouldn't they name those blasts? But the bone breakdown cells are osteoclasts, and they secrete this acidic type enzyme that creates this pit. It's called the resorption pit, and they create this basically breaking down of bone to release minerals, and then the osteoblasts come back through and remake new bone tissue over that spot, and that's how bone is formed, and in this case also broken down. Now, minerals have plenty of functions. We've already kind of danced on some of them and looking at how we process them, but technically structural and functional roles of nutrients or minerals are plentiful, starting at the cell and molecular level. All cell membranes are, what are they lined with? It's called a phospholipid bilayer. And so the phospho portion of that is important and gives a cell membrane its fluidity and polarity and interaction with other compounds, etc. Also phosphagens, so stored phosphagens like ATP, which we've heard this a ton now, but that's a stored phosphenogen, and the phosphate bonds allow for the rephosphorylation of ATP. So the releasing of that energy allows us to do muscle contraction and all kinds of things that we need ATP for, and phosphate is a big part of that. You have to have dietary phosphate to store in these molecular level structural compounds. Minerals are also in bone tissues and skeletal tissues. In our bones specifically, it exists as a protein, calcified mineral protein called hydroxyapatite. And in teeth, it's fluorohydroxyapatite. And you can kind of look at the difference here. Fluoride just provides a little additional layer of structure. So we don't have a whole lot of fluoride in our bones, but we have a ton of it in our teeth. And it's an even stronger mineralized tissue than regular bone. So that one in the teeth needs fluoride, but in the bone, not so much. Again, our bone has a lot of neat functional attributes. It's flexible, it's lightweight, it's incredibly lightweight for how strong it is. It can withstand all kinds of different compressive and physical forces. Minerals are also needed to sustain energy utilization, and we didn't talk a whole lot about copper, but we're going to talk about a few copper functions. Copper is one of those dietary nutrients we don't assess too much. We just get it in the diet from trace sources. It's ultra trace and our body conserves it. But copper is important for reducing enzymes. So we talked a lot about different metabolic processes where like glycolysis and how that leads to the TCA cycle or Krebs cycle, and how from there intermediates go into the electron transport chain. Well, all of these different metabolic processes and energy systems require these enzymes that transfer these electrons, and that's how oxygen is transferred, carbon dioxide is transferred, and all the little pluses and all the little electrons and everything that you see that makes carbon dioxide and oxygen needed and produced in metabolism relies on copper and iron containing enzymes that transfer all of those different gas compounds. So essentially, literally, minerals are needed to sustain metabolism and specifically energy systems. Minerals are also needed to sustain lots of just cell operations. And I know I already touched on this, so I won't beat it to death, but hemoglobin, it's an iron-containing compound that's in red blood cells. And I touched on that it transports oxygen, but the neat thing about iron is that not all minerals are ligand binding. Not all minerals as effectively and quickly bind oxygen. Iron and oxygen love each other. So iron just really is an important mineral because it's not only structurally important, it not only binds gases, but it's unique in its affinity for oxygen. So no other mineral can do it so effectively. We also know that we need dietary minerals for enzyme catalyst activity. So sometimes enzymes need a trigger or a start or an activation, and copper particularly does this. It's a metalloenzyme for a really important enzyme needed in collagen production, and specifically collagen cross-linking, which we talked a little bit about with protein and a little bit about even with vitamins, but it's an important function that requires these particular enzymes. And these enzymes need a little shove to get going by these different metals. So we also know that calcium is needed for muscle contraction. So all the different types of muscle cells, myofibrillar, all contractile muscle cells. So myocardial in the heart, skeletal, so like, quads and glutes, and even the autonomic, all the different muscle cells in the body. So calcium does this by when the body releases neurotransmitters, calcium takes this little piece of troponin and moves it out of the way, and that way myosin and actin can bind, which allows for the hook pull contraction and muscle contraction. So calcium literally is released into the cell. Its presence there is critical because it allows the binding of the hook pull for actin and myosin. Without calcium there's no binding to troponin. It doesn't move anything out of the way, and actin and myosin never bind. Muscles can't contract. And in the world of myocardial tissue, that means death. That sounded kind of insensitive, but when we're talking biology. We also know that minerals have protective roles. Specifically, zinc is always tied to immunity, and that's because it stimulates the production of a particular type of lymphocyte or immune cell. And I think that this is not a great representation. It looks like zinc is like poison or something. we have particular cells that have functions. And one of the functions of tyrosine kinase binding is because in this cell reaction, it releases like this toxic thing to pathogens. So it recognizes a pathogen, it releases basically what would you call, like a bug killer. And then basically those cells, the presence of zinc enhances the production of those cells. So zinc isn't like the actual, what's being used against pathogens, is that the presence of zinc allows those cells to produce more effectively. And then when there needs to be a response to a pathogen like a virus, our cells are more equipped to do so. We still really need to have a lecture on nutrition and COVID. Minerals also function to neutralize acids, particularly these that are showing, but the cations and anions create that balance of the negatives and the positives. And that also is really important, guys, for pressure balance. So that also, and we'll talk more about that in the water section, but where the charges go, the water goes. And so mineral distribution is important for water distribution, which goes back to blood pressure and all the different important, like osmotic is the pressure in the vascular space, and oncotic pressure, like the area between the cells and between the vascular space. So minerals are important for that, because without them being in the right proportion in the diet, they're not pulling water in the right proportion in those compartments either. They're also known for their free radical activity, particularly zinc and sometimes copper, for their role as a natural cell oxidant, copper oxide dismutase, superoxide dismutase. I don't know why I said copper oxide. But yeah, powerful cellular antioxidant, much like vitamin C, vitamin A, but probably even more powerful. So that's all we have for the functions of dietary minerals. And next we'll talk about imbalances. What are the measures when we know that we're inadequately consuming them? Mineral status. So when we're looking at mineral imbalances, we're looking at whether we have excess or insufficient daily dietary intake. And not a lot of people have mineral toxicities, but there are a certain amount of dietary minerals that we do tend to overconsume. One of those being sodium chloride. Those two kind of go together. Doesn't take a lot over the EAR to be in excess of what's recommended, because it doesn't take a lot to create deleterious changes with vascular function. Notably, the people that typically are on the higher end of this toxicity spectrum with sodium do report consuming a lot of processed foods, a lot of fast foods, and foods that are known and taste like they have salt added. Lots of calcium, iron, and zinc overloads, but these are almost never from natural dietary sources. They're from supplements and from added calcium sources, like you're having your calcium OJ in the morning, your calcium supplement here, and your calcium added yogurt there, and etc. And then fluoride. I did this to my kids. I didn't make sure they weren't, I didn't know about the whole fluoride thing, so I don't think I bought fluoride-free toothpaste, or I let them swallow a small amount of it, letting them manage their own oral hygiene. Anyway, little black spots will get on teeth if you get too much fluoride in the diet. There are also deficiencies with minerals in the diet. Less and less with enrichment fortification programs, iodized salt, and all those things. These aren't huge issues in our society, but in other countries where there aren't all of those programs and requirements, you do tend to see iron deficiency, zinc deficiency. It's not all that unheard of. Potassium, there's certainly a link there for people that don't get any fruit and vegetables, which is common definitely in the US. So potassium deficiencies aren't just like a clinical thing yet. We're not enough along, but we know that low fruits and veggies equals low potassium equals maybe low grade metabolic acidosis. Not equals, just doesn't help. And some people have naturally acidic environments. We'll get to it. Also, people who don't like the lactose or the dairy products are sometimes calcium deficient. And then lastly, vegans and vegetarians who don't consume meats and seafoods can sometimes be deficient in iron also. The status measures that we would kind of use to measure these include bone density. If a person's bone isn't very dense, we can only assume, obviously you guys, we're only talking about healthy adults. So outside of a person with a thyroid deficiency where we're having, tons of purging of mineral from the skeletal tissue, healthy adults where everything's functioning properly, if bone mineral density starts to get low, then you can assume it's because we're not adequately replacing in the diet. And low bone mineral density scores are expressed on this like DEXA measure of less than 1.08, and that could be indicative of calcium, phosphorus, or magnesium imbalances. We also can measure mineral imbalances in the blood, particularly like the proteins that carry iron in the blood and that carry other minerals. We can measure those proteins, for instance, transferrin. By the way, you're probably wondering, okay, she just talked about this and now she's talking about iron. I couldn't talk about all 15 minerals, all of their processing, all of their everything. So we're pointing out common ones. Like, it's very common to have a baseline nutritional assessment measure include, looking for iron deficiencies, because it's just common. So I included up here common nutrition assessments. Transferrin. That would be indicative of your iron intake. It would be that protein. If that protein's low, that means there's no iron to carry. We also know that hematocrit, or packed red blood cell volume, put in a spinner, the packed amount, if it's like a smaller amount than it should be, then you could potentially be iron deficient also. The measures are like the symptoms and signs and conditions and things that patients say in regards to these nutrient imbalances are things like cavities. I just don't have, this wound just won't heal. More seriously, and we're going to talk more about this in the nutrition for disease section, but hypertension. This is a serious metabolic disease that can be created by excess sodium. The more sodium, the more water pressure, the higher the amount of solute in the vessel, right? Also, you guys have probably heard of this, because when people go to the hospital in emergency situations, they get potassium and electrolytes, and this is because when those positive charges fall low, then people can have arrhythmias and problems with the electroconductivity of the heart, the electric part. Also, we will notice sometimes people have perceptible feelings to mineral deficiencies, like maybe even achy joints and bones, and more commonly, again, just general fatigue and tiredness, which is most oftentimes related to low-grade anemia. Some symptoms of anemia, I'm sure you've heard of these before, but really the main pressing one is paleness, fatigue, just a general low sense of energy, because you don't have adequate oxygen delivery, especially when you try to do something. There are also some apparent changes that you can see in people's physical appearance on the exterior. This one is genetic for my family. This spoon-shaped nails. If you have never had that in your family, you're probably like, that's really weird. Don't say that. But it's just like this curvature in the nail bed. But whenever I'm deficient, potentially in iron, and I know certain life phases, pregnancy, diet phases where I'm going somewhere and I want to cut calories, so with that comes other nutrients, it gets worse. So I've also noticed little I don't want to call them canker sores, but like a little tongue sores. Those will come when I'm certainly kind of tracking what deficiencies I might have. And they're tied with vitamin ones too, but hands down, the nail one is related to iron deficiency every single time. So zinc related to hair loss, and these are just, not always tried and true, but just things that are clinically noticed. The little spots I mentioned is called fluorosis, where they have little black spots on the teeth from excess fluoride consumption. It's over fluorosis. It's over fluoridating that hydroxyapatite. Okay, I'm talking too much, I know. Thank you for listening, you guys. I know that was a long lecture, but that's all I have on how much dietary mineral we need per day. It's not much, but it's very important. Where we get it from, the difference between plants and animals, how we process it, the main functions that it has, and what we see when we don't get enough of it or we get too much. Thanks for listening.